Hello, 8th grade. This video is about Newton's third law. We're going to talk about the third law, and we're going to couple that together with momentum, and then we'll be done with this chapter and we're almost ready for a test. We're going to make this short and sweet. You need to put your thinking caps on, though, because can be a little bit tricky. So here we are. We have a few vocabulary that you've seen in Quizlet. Make sure that you memorize all of these different words, okay? Newton's third law, force, pair, momentum, conservation of momentum. There might be a few others that I threw in for Quizlet. So, Newton's third law of motion is often said as, for every action, there's an equal and opposite reaction. Now, this can be a little bit deceptive because it's not, somebody pokes you and you react. That's not action-reaction. We're talking about force pairs that act together in the motion of two different objects. So what you need to recognize here is that when one object is applying a force on the second object will then apply a force back on the first, okay, in the opposite direction. So one really big thing that I sometimes wish they would kind of add here is that for every action, there's an equal and opposite reaction on two different objects. Okay, so keep that in mind as we're looking through here. We're talking about two different objects every single time. And so this is different than our net forces that we've been doing in the past because those are always on one object. We're talking about interactions. So here's an example. Anytime a person pushes against a stationary object, like when you take a step, all right, you have the pushing on the grass that you're doing, and then the grass has to push back on you. And if that doesn't happen, then you can't go anywhere. And so you have these two interactions that are happening. Okay, so here's another one where we're talking about a different set of motions. You have the action force here is where the air coming out of the balloon, that's kind of your action force. And the reaction is that the balloon goes forward. So it's important to recognize kind of which one of these is going to happen first, because you'll have some practice problems like that. You're going to have one force that happens first, and then a reaction force is going to be equal and opposite in a different direction. And that can sometimes cause motion. Now, this is different because before we said that you have to have unbalanced forces and where one force is unequal to cause motion, but this is two different objects, not one. If you analyze just one of these objects, then there is an unbalanced force acting on it. But when you put the two together, the forces are equal and opposite. Okay, so keep that in mind, equal and opposite. Now, if the forces of a force pair always act in opposite directions and they're always the same strength, we might think that they cancel each other out. But like I said, they do not cancel. Okay, they do not cancel each other out because they're on different objects. So action is equal to reaction, but they are on, this one's on the person, this one's on the boat. This is an example of a person who's about to jump off. They jump off the boat and it makes the boat do what? Well, it's going to go forward. Okay, so action, reaction. All right. Okay, same thing again with the rocket. And this is just another way of saying it. For every force, there is a reaction force that is equal in strength but opposite in direction of the action force. So action, rocket fuel comes out, reaction, rocket goes forward. Okay, so I want you to think about for a second the answer to this question: why don't the forces in a force pair cancel each other? Pause and think about it if you need to. Okay, so the question is, or the answer is, because they are on different objects. Okay, if you have equal and opposite forces on the same object, they cancel. Different objects, they don't. Now we get into momentum. And this is it's often just paired with Newton's third law because we're talking about different objects interacting. And momentum, when you take your force and your mass and you hit it against something else, you have those force pairs, and momentum has to do with how hard it is going to be to make those objects stop moving. Okay, that's kind of an easy way to think about momentum, is how hard is it going to be to make something stop. The word momentum comes from the Latin momentum, which means movement or impulse. We are going to calculate momentum here, and you need to memorize this equation, P equals m times v. Now, momentum is P, and that'll be hard to remember, but the others aren't. M is mass and V is velocity, and you've seen those before, okay? Now, you might end up having to use different versions of this where you solve for mass and you solve for velocity, but I'll give you those if you have to do that. It's easy. You just divide by the one that you're not looking for. So, you know, it ends up being V equals P over M, and M equals P over V. P is always on top. So that's pretty easy, but I'll give you those. Okay. So you've seen this before. I won't dwell on it too much, but you need to always think about what you're given, figure out what you need. Once you figure out what you're looking for, then you plug it into the equation, and your units here at the end, notice they're going to be kind of wacky. We just have the kilograms from the mass and the meters per second from the velocity, and we just put those together, kg m over s. And I might ask you to you know, choose which unit goes with what quantity, but you won't, in your problems online, you'll just have to put in the number, okay? All right, so thinking about this in terms of going back to Newton's second law, there's something that should be noted here. The force on an object, according to Newton's second law, is the mass times the acceleration, if you remember right. So the more force that you have, the more acceleration that you have, okay? This is also the change in the object's velocity. Now these quantities are similar to P equals mv. All right, so if we compare the two, if momentum is the product of mass and velocity, and the force is talking about mass and acceleration, we're talking about how its momentum changes in this because of the force. And so that's kind of something to think about here. Momentum and Newton's second law are very closely related. And it's closely related to Newton's third law, like we said. Now, our Newton's cradle, you saw this in the video that we watched the other day. When we talk about things colliding or hitting each other, one object is transferring momentum to another object. And so the momentum of this one goes to this one, and that one, and that one, and then it makes this one go up with the same momentum that this one started with before the first one started with, before it ever hit it. So we're talking about the conservation here, and that means that things are kept the same. Now, one question I get is, well, do they ever stop moving? Do the balls ever stop moving? Well, you guys have seen it in my classroom, they do. But in our classroom, the strings are very off kilter, and the thing is wobbly, okay? And so we don't have a perfect situation. We also have air resistance, and air resistance will slow these things down over time, as will the wobbliness and the imperfect strings. And so those are all kind of types of friction that slow it down. If we set one of these things moving in space, it would go for a very, very, very long. All right. Now, according to the law of conservation of mass, or I'm sorry, momentum, the total momentum of a group of objects has to stay the same unless something like an outside force is acting on the objects. Friction is often this outside force that will make conservation of momentum not actually occur. But in a perfect system, it does occur. And so if you think about the pool balls, you're going to strike this ball and it's going to come and strike this ball with the same momentum, and oftentimes all of the momentum in this one gets transferred to the yellow ball, and so it will have the same speed that the first one did because they're similar masses. Okay, so when you think about the momentum of the first ball, it's going to equal the momentum of the second ball, and if they have the same mass, m1 and m2 are the same, then that velocity ends up being the same. Okay, so that's how conservation of momentum works. Now, an elastic collision is when the objects will bounce off of each other. Okay, that's just like what you saw with the pool balls. They bounce off of each other and the momentum is transferred. Okay, but that's not what always happens. In an inelastic collision, your objects might stick together. Okay, and so like in this case, the car sticks to this other car and they'll both as a group move forward. And that's what we call inelastic collision. Now the total collision of that will still be the same. The momentum of the first car, P1, will equal the momentum of both cars together at the end because they're then kind of considered one object. Okay? Now, in both elastic and inelastic collisions, the total momentum of the objects is always the same. And so this is kind of what I was saying before, so I won't repeat it too much. But if your first ball has momentum m and v, and your second ball starts with 0, then after the collision, you have the first ball ending up with momentum 0, and all of the second ball has the momentum now. Okay, so it's just same thing as what I said before. And that kind of brings us to the end. You need to understand this conservation of momentum concept, though, as to where we're saying the momentum of a system before equals the momentum of a system after. Okay? So that is Newton's second law and momentum, and hopefully this all makes sense. If it doesn't, ask questions. Thanks.